All right, now we're moving into year 13 content. So if we expand on bill, now suppose that this is the current and the field is going this way. This is the field. So this is the magnetic field. You've got current going in, and suppose the angle is here. Now you need to work out the perpendicular angle, don't you? So the perpendicular angle is sine. So that is B sine theta. So over there is B sine theta. So how would you work out the force now? So the force is equal to the BIL sine theta. Right, so let's draw a few examples. So if the field lines are going this way, so these are field lines, assuming that these are all equally spaced out, and you've got the current going here, so this is the current, that's B, B for magnetic flux density, and what is theta in this case? Theta is 90. So F in this case is equal to B times I times L times sine 90. And what's sine 90? Sine 90 is 1. So F is equal to BIL. Okay. Now if theta is at an angle, so let's just draw the field lines. And then suppose the current is going in this direction. Then using BIL, suppose theta is 30. So if theta is 30, what is the force? So F is equal to BIL sine 30, and sine 30 is a half, so it will be a half times BIL. So it's only when the magnetic field is perpendicular, that's when the force is at a maximum. When perpendicular. Okay, so maximum when it is perpendicular. What happens if it's 0? If the field lines are like so, and the current is here, so say that's the current. Theta is now equal to 0, and F is equal to BIL sine 0, that gives you 0. So when it's parallel, you get 0 force. All right, so let's try a question. So if, let's just say L was 0.71 meters, I was equal to 4.1 amps, theta is equal to 32 degrees, and you know F is equal to 0.17 newtons. Okay, so try it for yourself. Just rearrange the formula and see what you get. This is just a mathematical exercise. So, and you want to work out B. All right, so we write the equation first. F is equal to BIL sine theta, and F is 0.17, and that is equal to B times, you know, I is 4.1, that's 4.1, and you times L, which is 0.71, and that is times by sine 32. Okay, so B is equal to 0.17 divided by 4.1 times 0.71 times sine 32. All right, so let's put the numbers in and see what we get. All right, so it's 0.17 divided by brackets 4.1 times 0.71 times by sine of, make sure it's in degrees, sine 32, brackets. You get 0.11. So 0.11 Tesla. Flux linkage at an angle. If we write down, so here are the field lines and the coil of wire here. So let's just say that this is the coil. This is the magnetic field lines. So that's the coil. Now, let's draw the normal to the coil. So the normal is 90 degrees to the coil. So this is 90 degrees to the coil. Now you don't want the angle between the coil and the magnetic field lines. So this is not the angle. So this is not the angle. You want the angle between the normal and the magnetic field lines. So if we were to extend this, let's extend this. And let's carry on. You want this one here. So you want this angle there, not that angle there. So you want so this is the coil. You've drawn the normal to the coil, and you want the angle between the magnetic field lines and the normal to the coil, not the coil and the magnetic field lines. So it's this one that you want. And what is the equation for magnetic flux? If you remember that magnetic flux density is B, so B is magnetic flux density B times A will give you magnetic flux. However, we're missing a component, so we're missing a cos theta. So the proper equation is that the magnetic flux is equal to BA cos theta. Now, what is the equation for flux linkage? So this is magnetic flux. So magnetic flux is how many field lines there are coming out of the surface. Magnetic flux is how many field lines there are per area. So magnetic flux, sorry, this one. So magnetic flux density is how many field lines coming out per area. Magnetic flux is how many field lines coming out of the surface. And the proper equation is using the cos theta. So what is magnetic flux linkage? So magnetic flux linkage is equal to NBA cos theta, where N is the number of coils. So the number of coils, so let's just say that's 1, 2, 3, 4, 5. 5 coils. So here you have N is equal to 5. N is the number of coils. All right, so let's try a mathematical exercise. So what happens if N was equal to 200? So 200 coils, 200 turns, and you've got the length of the sides as, this is a rectangular coil. So you've got the dimensions. So the dimensions is equal to 5 times 6.51. 5 times 6.51 centimeters. That is also centimeters. And you've got the magnetic field strength or magnetic flux density is 8.56 times 10 to the minus 3. So if you know that B is equal to 8.56 times 10 to the minus 3 Teslas, and then the normal. So you got 12.6 degrees, and you know that theta is 12.6 degrees. What is the flux linkage? So what is flux linkage? All right, so let's just rearrange. Do we need to rearrange? We don't need to rearrange. So the equation is what is NBA cos theta. So you know N is 200. You know B is 8.56. 8.56 times 10 to the minus 3. Now the area, you need to convert that into meters. So that will be 0.05 times 0.0651. So 0.05 times 0.0651. That's the area. And you times it by cos of 12.6. All right, so that's the working out. Let's see what we get on the calculator. So 200 times 8.56 times 10 to the minus 3 times 0.05 times 0.0651, and then you're multiplying it by cos of 12.6. That will give you 5.4 times 10 to the minus 3. 5.4 times 10 to the minus 3. And what are the units? It will be in Webers. Okay, so the units for magnetic flux is Weber. And because all you're doing is multiplying by a constant, magnetic flux linkage is still Weber. So the units for magnetic flux linkage is Weber. The unit for magnetic flux is Weber. However, magnetic flux density is in Teslas, T.